So in today's lecture, we are going to talk about ion exchange chromatography. So what exactly ion exchange chromatography is about? So as I mentioned in the last class that you can discuss the ion exchange, read more about the ion exchange chromatography from these links. So this particular one is a very good and detailed link. Okay, and if it's very useful from an experimentalist perspective. The second one is really good for theoretical understanding from the mid-sized bio, very good website for a biologist, biotechnologist. And third one is a brief one, but it's very good for an overview understanding. Okay. So what are exactly ion exchangers and their chemical nature? So ion exchangers are are polymeric molecules that have charged groups. So anion exchanger is something that can uh, bind to anions, okay, meaning it has internally placed positively charged groups. Cation exchangers, as the name suggests, are bind to cations, so it has internally placed negatively charged groups. Okay, so these are some of the structures of the cation exchangers. More on the next slide. So this can have uh, uh, quaternary amines. This is also a quaternary amine. Okay, where the N is has three substitutions, and you can have the CH3 group and a plus charge here, and NH CH2 groups of plus charge here. This is a cation exchanger which has a sulfonate ions, a common cation exchanger, and another one is a carbonate ion based cation exchanger or carboxylate ion and ion based cation exchanger. So what are the four stages of ion exchange chromatography? So ion exchange process can be separated in four basic stages. The first one is equilibration, application of sample, elution, and regeneration. Okay, so to understand each of this, what exactly does this mean? So first one is preparing an equilibrated resin. So to understand this, let's just assume that we are trying to separate three positively charged proteins having three different charges. Okay, so here they are. Okay, so here they are. So one have three positive charges, one have two positive charges, and one have one positive charge. Okay, so we are trying to separate them by utilizing their different charge properties. Okay, so the resin that we'll be utilizing for this property should be a cation exchange resin, meaning it internally it should have a negatively charged. So it should be one of these two. Okay, it should be one of these two here. Okay, which one I'll come back to that question. So what is going to happen here is that the equilibrated resin here will have some positive charges bound to it, meaning these positive charges are typically sodium cation. Okay, so nothing can be completely negatively charged. There has to be a counter ion present. So typically this should be equilibrated with a sodium cation in its default state. Okay, so this is neutralized and with the presence of the sodium. So at this stage, when you apply the protein or application of the sample, so all three proteins will go into the column, okay, and they will bind to the resins. Okay, so resins, what will happen is it will cause replacement of the sodium ions, and sodium ions will come out from the solution as a counterion of the anion of the proteins, and the proteins will be stuck to the column. Okay, so you can see that the plus is the has the least charge, so that would come out that would probably travel most, followed by the double positive, followed by the triple positive. So triple positive will bind to a lot of anionic groups and it will be the least traveling groups. The double positive will travel a little more because it will probably bind to a little less number of resins, and the single positive would be bound to only one group, so it should have a lot of ease of traveling. If any fourth protein is there, which is neutral, that would be even before this. If there is any fifth protein is there, which is negatively charged, so that would not even bind. So negatively charged will come out probably even before the neutral ones. Okay. So now your protein is separated from the unwanted protein, which is, let's say, a negatively charged protein, a neutral protein. So next you need to separate your bound proteins, that is the positively charged proteins, and different positively charged proteins in this case. So in this case, then how do you separate the charged proteins one at a time? So first, you apply a low salt condition, that is, let's say 0.4 molar sodium chloride. So zero point 0.4 molar sodium chloride will not do much to separate your triple charged protein, or but it will be good enough to compete with the single charged protein, and it will replace that, and so your single charged protein will try to come out. So this is your single charged protein. Okay, we are monitoring their elution by using UV 280 nanometer, because your proteins absorb at UV 280 nanometer. So this is your single charged protein coming out. Then as you increase the salt concentration, so your double charged protein will now face competition, and that will next come out here. Okay, so this is your double charged protein. Next, as you increase the salt even further, now there is a lot of cations present, so all of the ions now would be ion exchangers would now be replete with the sodium. So your a triple charged protein also will start to come out. So that will be this one over here. Okay, so this particular picture is, so it says like if you increase the salt concentration, this side is the absorbance, A260, A280. This is the salt concentration. So with the increasing salt concentration, you three proteins come out. So this particular picture is called chromatogram. This is called chromatogram. Okay, so this basically tells you that how separated your proteins are. So if you can also collect them in test tube. So this you can collect in a test tube. This peak, when it is starting to come out, you can collect in a test tube. This peak it collect in a test tube, and your proteins will be separated from one another. Okay, it's a standard method for protein separation using ion exchange chromatography. So how do you choose what ion exchangers to use? So there are a bunch of them available from industry. And you can see these descriptions on how to choose which one and which one would be appropriate. So diethyl aminoethyl, or DEAE, is a weak anion because it is a ternary ammonium salt, meaning that it has only three ethyl groups and one H plus groups. So its pH functional range is less. So it is a weak anion and most likely will bind to weak what should I say weakly charged cationic protein. Okay. This particular one is again a ternary cation, ternary ammonium cation, proteinated cation, also binds to weak anion. The quaternary amine, in contrast, is a strong anion and it has a higher pH range at which it binds. So this is a more strongly present positive charge. Okay, and it would be operational in all pH. So why the pH comes into the picture? Because as you increase the pH towards more alkaline pH, this H plus will be gone. So this will equilibrate into NCH2, sorry, C2H5 whole 2, and it will become neutral. Okay, so your resin is no longer cation. So at alkaline pH, this will not be neutral. But this is a permanent positive charge, so there is no H plus to be replaced. So this is a operational in all functional resins. Similarly here, the carboxymethyl is a weak cation because below pH 5, this COOH will form COO minus will form a COOH. The methyl sulfonate, on the other hand, is a strong cation because this is a stronger acid. So this will be operational in a bigger pH range. This is even stronger acid, so this will be operational in a slightly higher pH range. Okay, and so on. Okay, so this lets you control the weak anions lets you control the flow in a more delicate way. Okay, but this is more of a straightforward application, so this can be is very easy to handle, and it can be optimization is much simpler. These cases you have to play around with the pH a lot. Okay, so this takes a little more delicate balance. So how do you now the other factor is now we learned the charge of the ion resins. So how do you control the charge of the proteins? So this depends on something we know already, that is the Henderson-Hasselbalch equation. So Henderson-Hasselbalch equation, if you remember, the charge of the amino acids are dependent on the pH, right? So you have side chains on which you can control the charges depending on the pH. The same you can do it for peptides and proteins also. So I'll give you an example, not on this one. I will use this particular one. So this particular one has is a protein of three or a peptide of three residues: arginine, aspartic acid, histidine. So the side chain. So this part is the arginine part. Okay, this part is the arginine part. Then followed by the aspartic acid part, which is right here, followed by the histidine part, which is right here. Okay, so I have put the pKs of the various side chains and the groups that would be relevant. So that this is N-terminal. So then this should be considering, we should be considering its pK. Okay, we should be considering this pK also. So I forgot to put this one. This should be around 3.7 or so. Then you have the pK of the okay, it is over here. Sorry, this is here. Sorry about that. Okay, so this pK is this pK is peak 6.0, and this particular one has a pK of 2 point something, 2.3 or so. Okay, so by mistake, this pK is this, and the carboxylic acid pK is this one. So I asked a question: what is the charge of this peptide at pH 7? So we have to find out this using the equation that if the pH is less than the pK, it ionizes less than 50%. If the pH is more than pK, it ionizes over 50%, and the ionization happens. Ionization means the Ha loses its H plus to form A minus. Okay, that is the ionization. So let's see what is the structure at pH 7. So at pH 7, for this one, it is still pH is less than pK. Okay, so for this one, sorry, pH is still yeah, less than pK. So this will stay ionized, and this will have retain its protons. Okay, so this will stay NH3 plus, because for this pH equals to 7 is less than its pK equals to 12.4. Okay, and this is NH, and you have the NH3 plus, which is right here. Okay, for this one also pH 7 is less than its pK, which is 9. Okay, 9.04. Then you have the side chain carboxyl from the aspartic acid. So aspartic acid side chain, now this will, for this the pK is less than its pH. Okay, so this would become CO minus, because pH 7 is over its pK, which is 3.65. Okay, and you have the NH, and then you have the histidine group, which is over here. So imidazole group, not the histidine, imidazole group, sorry for the mistake. So this will also lose its pH, because the pH 7 is more than its pK of 6. Okay, so that is that. And finally we have the COOH. Okay, that will also be losing its H plus, because it's also the pH 7 is more than its pK 2.3. Okay, so if you calculate the net charge, so this is plus 1 from here, plus 1 from here. So we are calculating net charge, plus 1 here, plus 1 here, minus 1 from the carboxyl, this is 0, and minus 1 from this carboxyl. So the protein is neutral. Okay, the protein is neutral, or it will be mostly neutral. But you can similarly, you can, if you increase the pH more, some more groups will ionize, and you can calculate the net charge. So if you want to do a more quantitative calculation, you have to do a Henderson's equation to find out what exactly it is. Okay, but this is the basic chemistry. So, how to control the charge of the protein? So, using the Henderson's equation, you can control the charge, and we have to use the basic idea that the pH of the solution, the isoelectric point is the pH at which it is neutral, right? So, if the pH is lower than its pi, okay, it becomes positively charged. So this is how you already discussed and showed it to you. If the more lower the pH, the more positively charged it becomes. If the pH is higher than the pi, it becomes negatively charged. The more higher the pH, the more negatively charged it will become. So you can calculate this by Henderson's equation. We have shown this. So let's see how this is operational. So for carbonic anhydrase, the pi is 7. At pH 4.8, it is below its pi. So it is this particular condition we are referring to. So it should be positively charged, which we are seeing here, right? At pH 7.2, this is just above its pi. So it is this condition. So it is almost neutral, but slightly negative, minus 0.4. At pH 8, it is a little away from its higher than its pi. So the negatively charged has increased. It is minus 2.7. So same pattern you can see for carboxypeptidase, chymotrypsin, lysozymes. So all of them are following this principle. Okay, so now let's say you have a cation exchange resin. Cation exchange resin, again, it is negatively charged groups. So in this, you are adding this mixture of this protein at pH 7.2. Okay, so we are doing it at pH 7.1. So I may have missed the pH. Yeah, this should be 4.8. My mistake. This should be 4.8. I'll correct it when I do this. Okay, so the buffer pH is kept at 4.8, and all this mixture of the protein, carbonic anhydrase. Okay, so Ca, carboxypeptidase, Cb, chymotrypsin C, and the lysozyme is being applied. Okay, and all of them, the buffer pH has been kept at pH 4.8. So their charges are plus 16, plus 12, plus 9, and plus 14. Meaning that which one will bind to the cation exchange, the negatively charged resins more? That would be the carbonic anhydrase. Okay, so the carbonic anhydrase should be having the strongest binding. Okay, so and the rest of the proteins, they will elute in the order of the less charge. So at this case, chymotrypsin has the least charge. So chymotrypsin will elute first because it has the least binding to the resins. So this will be followed by the carboxypeptidase B, because that is plus 12 charge. Okay, so chymotrypsin has plus 9, carboxypeptidase has plus 12, and the next to elute would be lysozyme, which has plus 14. Okay, so that would be the order of elution. At last, if we increase the salt probably high enough, we would be seeing the elution of the carbonic anhydrase. Okay, so Ca would be eluting at the last. So that has a charge of plus 16.5. So I'll show one more example. So in this case, again, so is a typo. This should be pH 7.2. So my question is, which protein will bind first and which protein will elute first? Okay. Again, you can use the same logic. So this is minus charge, minus charge, minus charge. So at pH 7.2, which one does have the most positive charge? So that would be the lysozyme, right? So lysozyme will have the highest binding. Okay, so lysozyme will bind to the beads most. Okay, so which one will elute first? So at this stage, This is the most negatively charged, so this will have the least binding to the beads. So carboxypeptidase will elude first because it has a charge of -3.3. So that would be followed by carbonic anhydrase, because carbonic anhydrase is almost neutral, slightly negative. That would be followed by the chymotrypsin, because it has slightly higher positive charge, but definitely not as positive as the lysozyme. Okay, and the lysozyme, if we put a salt, good salt concentration, then lysozyme will come out. Okay, same I have done for pH 8 also. So this is pretty much the theory about the ion exchange chromatography. So you can go over this, and I will have a more discussion in the actual.